Welcome to my lecture on sampling. So I am going to introduce what is meant by a sampling. What is sampling theorem? How sampling can be used to convert a continuous time signal into discrete time signal. Sampling is the process of converting analog signal into discrete signal. So as we already stated that sampling frequency or sampling rate is how many number of times per second the signal will be sampled. So this is an important concept because it restricts to the highest frequency that is present in the signal. This is the simple way of representing continuous time signal, which is being converted into discrete time signal using the process called sampling. So what is the principle of sampling? The main principle of sampling is a simple multiplication. The analog signal is given to a multiplier. Another input of the multiplier is periodic signal sequence, which may be a impulse train or maybe a pulse train. So if I give an impulse train, it becomes a instantaneous sampling or impulse sampling. If I give a periodic signal, it will be a practical sampling, also called as either flat off sampling or maybe natural sampling, generally we consider. So what is a sampling theorem? Sampling theorem has been formulated by the scientist called Nyquist in 1924. Generally formulated the same theorem in 1928. So this sampling theorem is also called as the Nyquist theorem. So what the Nyquist theorem says? So the sampling theorem says that the minimum sampling rate at which a continuous time signal needs to be uniformly sampled so that the original signal can be completely recovered or reconstructed by these samples alone. So generally the sampling frequency is also called as Nyquist frequency or Nyquist rate. So minimum sampling frequency is called Nyquist rate or Nyquist sampling. So generally for any sinusoidal signal, sin 2 pi of t is a sinusoidal signal, let us consider, where f is the message signal frequency. Here we are considering the sampling frequency is always be greater than or equal to 2 times the message signal frequency. Then you may be able to recover the original signal from the samples we have been generated using sampling theorem. That's what the sampling theorem is. So here we are talking about a sampling theorem for low pass signals. As I already told, if the continuous time signal contains no frequency components higher than omega h, then it can be completely determined by uniform samples taken at a rate of fs samples per second, where fs should be greater than or equal to 2 into omega. So in terms of sampling period, if I want to represent, so t should be less than or equal to 1 by 2 omega. This is suppose if more number of components will be there. Let us say sin 2 pi f1t plus cos 2 pi f2t, something like will be there. We try to calculate the maximum frequency among f1 and f2. So that maximum frequency is called a message signal frequency, which is band limited in nature. So that by using that maximum frequency, you can calculate the sampling frequency. Fs should be greater than 2 into f maximum. Generally, we do like that. So this is a simple principle here, as I already taken the low pass signal x of t, and delta t is the impulse train. If I multiply these two, I will be getting the signal like this. Or you can also use the frequency domain. So suppose let us say frequency spectrum of x of t is equal to x of omega. If I combine these with the Fourier transform of delta t, Fourier transform of impulse train is always be an impulse train. When impulse train is multiplied with the spectrum, I will be getting the output, sampled output would be look like this. So here we use 3 cases. Before talking about 3 cases, first of all, we should know what is the mathematical representation of that particular sampling process is going to be. So because the delta t is being represented as a impulse train, Fourier transform of any pulse train or any period signal can be calculated by taking the trigonometric Fourier series of the signal or exponential Fourier series of the signal. So here we are considering a trigonometric Fourier series. So delta t may be represented as a0 plus sigma n equal to 1 to n or 1 to infinity an cos n omega st plus bn sin n omega st, where a0 and b0 and an can be represented like this. a0 will be 1 by t minus t by 2 to plus t by 2 delta t dt will give you 1 by ts. Similarly, an will be represented as like this, will be 2 by t. So I can write bn may be represented if I write 2 by ts minus t by 2 to t by 2 delta t sin n omega t dt is always be 0, because sin 0 is 0, automatically this becomes 0. Only an and a0 will be existing. So after substituting those values in the delta t, I can have 1 over ts plus sigma n equal to 1 to infinity 2 by ts cos n omega st plus 0. So if I substitute this delta t in the expression y of t equal to x of t into delta t, I can have x of t into 1 by ts sigma n equal to 1 to infinity 2 by ts cos n omega st. You can write. So from there I can have 1 over ts x of t plus sigma 2 into sigma n equal to 1 to infinity cos n omega st into x of t. So this can be written y of t equal to 1 over ts x of t 2 cos omega st x of t plus 2 cos 2 omega st x of t. If I just expand the summation like this. So if I take a Fourier transform on both sides of the equation, I can have y of omega equal to 1 over ts x of omega plus x of omega minus omega s plus x of omega plus omega s x of omega minus 2 omega s plus x of omega plus 2 omega s and so on you will get. So entire this thing can be written as sigma n equal to minus infinity x of omega minus n omega s. So this is the general process of calculating the Fourier transform of a particular signal. So this is this may be represented in this form. So once you represent the x of omega, sampled version of the signal like this here. So you can reconstruct the original signal from its samples based on the sampling condition we are considering. So based on fs is greater than 2fm or fs equal to 2fm or fs is less than 2fm. When fs is greater than 2fm, it is oversampled and the spectrum of each spectrum is away from each other. This is omega s and this is 2 omega s, this is minus omega s, and there is no overlap between one sample with other sample. You may be able to recover the original signal from by using a low pass filter. So you may be able to reconstruct the signal very easily. Suppose if fs is equal to 2fm, that is fs is equal to 2 times the message signal frequency, or I can say perfect sampling is being done. Also, you may be able to recover the original signal from its samples. Suppose fs is less than 2fm, means fs is less than 2 times the message signal frequency, then the sampling is called undersampling. when the sampling is done with this sampling rate, so there may be a chance to have this sample is overlapped with this sample and this sample is overlapped with this sample. Under that circumstances, it is not possible to recover the original signal as such. So because of the overlapping of one sample with the other sample, means only a part of the signal will be recovered and remaining part of the signal may be lost because of a simple effect called aliasing effect. So that we will discuss later, maybe after 2 to 3 slides. Right? So how to reconstruct the original signal? So reconstruction of the signal can be done if omega s is greater than 2 times the message signal frequency or 2 times the bandwidth. So the replica of x of e power j omega do not overlap with the frequency domain. So if there is a overlap, there could be a possibility to have aliasing. So you may not be able to recover the signal. So to avoid aliasing, what generally we do is the sampling frequency omega s should be greater than 2b. So for that, I am using a simple filter called low pass filter. So xs of t is the sampled version of the signal equal to x of t into p of t, or maybe s of t we can write. What is called p of t is the periodic pulse signal or periodic impulse train, you can write. So will be passed through a low pass filter. You can get a x of t from its samples if omega s is greater than 2b. So this is the low pass filter I am using. So if I pass the same signal through a low pass filter, this signal is passed through this low pass filter, I can recover the original signal called x of omega. So the dotted version of the signal is called low pass filter. So this part of the signal may be recovered and remaining samples will be rejected from the sampled version of the signal. So you may be able to recover the original signal. Right? So that is sampling frequency omega s equal to 2b referred to as Nyquist sampling rate, which I have been already explained previously. Now you can also recover mathematical expression also can be represented like this. So to interpolate the signal, the frequency response of the low pass filter or interpolation filter is called h of e power j equal to t between minus b less than omega less than b, which is equal to 0 elsewhere. So if the impulse response of this filter is given by, so suppose if I take an inverse Fourier transform to this signal, then h of t becomes bt by pi sin bt by pi by bt by pi, which may be represented as sin bt by pi into sinc pulse, sinc of bt by pi, and t varies from minus infinity to infinity, I can write. So you can recover the signal by just simply convolving h of t with xs of t. Xs of t already defined. H of t is the low pass filter. When low pass filter is convolved with xs of t, I can have integral minus infinity to infinity xs of tau h of t minus tau d tau. And xs of tau is already been defined as sigma n equal to minus infinity to infinity x of nt into delta t minus nt multiplied with h of t minus tau d tau. So this can be written sigma n equal to minus infinity integral minus infinity to infinity x of nt delta t minus nt h of t minus tau d tau. Using the shifting property of the impulse function, I can have delta t minus nt into h of t minus tau can be written as h of t minus nt. So I can have n equal to minus infinity x of nt h of t minus nt you can get. Similarly, the same interpolation can also be represented in a diagrammatic form like this. So these are so many number of samplings. So the sinc function may be represented like this. So y of t equal to bt by pi sigma n equal to minus infinity x of nt sinc of b by pi into t minus nt. So this can be represented because here we have so many number of summations. You can sum it up and you can recover the original signal from its samples, which is being described previously. So this is an interesting graphical interpretation shown at the right actually. This formula describes a way to perfectly reconstruct the signal from its samples. So the main application here we use is in A to D conversion or D to A conversion, the sampling process generally be used. So as I already told, aliasing is another problem in sampling. So whenever a signal is time limited signal and cannot be band limited, since all signals are more or less time limited, they cannot be band limited. Therefore, we must use a low pass filter for reconstruction of the original signal. Before reconstruction of the original signal, we use a filter called anti-aliasing filter typically, and this generally be used in analog to digital conversion. So if the signal is not band limited, the distortion will occur, and that when the signal is sampled. So that is referred to as aliasing. So to avoid this aliasing, we use an anti-aliasing filter before processing the reconstruction of the signal. So this is the original signal x of omega. So if this is the sampled version of the signal, there is a overlap one signal with other signal, and this because of this overlap, some part of the signal may be missing. So due to aliasing. To avoid aliasing, you have to use the frequency fs should be greater than 2ff. So this is the simple process of sampling process. So we try to solve some of the problems related to the sampling. That is, we have given a signal. We are asked to find the Nyquist rate and Nyquist interval of a continuous signal here. So this is the signal x of t will be in the form of cos A, cos B form. 2 cos A, cos B can be written as cos A plus B plus cos A minus B I can write. So here 1 by 2 pi is that 2 cos A, cos B can be written as 1 by 2 into cos 4000 pi plus 1000 pi t plus cos 4000 pi t minus 1000 pi t. So you can have 1 by 4 pi cos 500 pi t plus cos 300 pi t. So this is what is called equation 1. And here to find the sampling frequency of such signals, sum of 2 signals will be there. So I can have like this, x of t equal to a1 cos omega 1t plus a2 cos omega 2t. So this can be written from a1 and a2 are amplitudes, omega 1, omega 2 are angular frequencies. When by comparing the equations 1 and 2, we get omega 1 equal to 5000 pi, omega t equal to 3000 pi. From there, you can calculate f1 equal to f2. f1 equal to 2500 H, f2 equal to 1500 H. So because 2 frequencies are there, we try to calculate the maximum of these 2. So that highest frequency component is called message signal frequency. So f max equal to max of f1 comma f2. That is max of 2500 comma 1500 give you 2500 H. Hence the Nyquist rate 2 into f max equal to 2 into 2500 equal to 5000 samples per second. So the Nyquist interval equal to 1 by fs equal to 1 by 5000 equal to 200 milliseconds. So this is one problem I can do it. So another problem is a real valued continuous time signal x of t is known to be uniquely determined by its samples when the sampling frequency is omega is equal to 10 power 4 pi radians per second. Find the value of omega when x of omega is guaranteed to be 0. So in the previous case, we calculated the sampling frequency. Now, here omega s is being given. You are asked to find the value of message signal frequency under the condition that the x of omega is guaranteed to be 0. So for that, according to sampling theorem, omega s should be greater than or equal to 2fm for avoiding the aliasing. So if x of omega equal to 0 for omega is greater than omega s. So for guaranteed to be 0, x of omega should be 0 for omega is greater than omega s by t. So under that circumstances, omega s is already 10 power 4. I can have omega should be greater than or equal to 10 power 4 by 2 into pi, because omega s is 10 power 4 divided by 2, 10 power 4 by 2. So you will be getting omega equal to 5 into 10 power 3 pi radians per second. So this is how I can solve the problem in this way. Another problem is, so here we have been given a same continuous time signal obtained at the output of the low pass filter with cutoff frequency 10 power 3 pi radians per second. If the impulse train sampling is performed on signal x of t, which of the following sampling periods will guarantee that x of t may be recovered from its sampled version using appropriate low pass filter? So here we have been given different times. Ts equal to 5 into 10 power minus 4 seconds, Ts equal to 2 into 10 power minus 3 seconds, Ts equal to 10 power minus 4 seconds I have been given. So as we know that the sampling frequency is being represented as omega s is greater than 2 omega, that is 2 into 10 power 3 pi radians. That is what is called omega s, already been given as omega s equal to 2 into 10 power 3 pi radians per second. So here the sampling frequency fs equal to 1 by ts equal to 1 by 5 into 10 power minus 4, because the time is being given as, this is what is called 2 into 10 power 3 is the what is called frequency of the signal. So and omega s equal to 2 pi of s, 4 into 10 power 3 pi radians per second. Similarly again fs equal to 1 by ts, second, for the second case I am considering. So here 1 by ts, 1 by 2 into 10 power minus 3 equal to 500 Hz. And omega s equal to 2 pi f equal to 10 power 3 pi radians per second. Similarly for third one, fs equal to 1 by ts, 1 by 1 into 10 power minus 4, 10 power 4 Hz. So I can have omega s equal to 2 pi f equal to 2 into 10 power 4 pi radians per second. So from the above analysis, by calculating fs for case 1, case 2, case 3, it is clear that 1 and 3 satisfies the sampling condition, but second one is not satisfying the sampling condition because of the aliasing problem. So here we can also have another problem similar to that. Find the Nyquist rate for the continuous time signal given below. X of t equal to sine 4 into 10 power 3 pi t by pi t. So if I take Fourier transform to it, Fourier transform of x of t equal to Fourier transform of x of pi t, Fourier transform of x of sine pi t by pi t equal to x of omega, which is equal to 1 for modulus of omega is less than tau, equal to 0 modulus of omega is greater than tau. Substituting the value of this tau equal to 4 into 10 power 3 pi radians per second in equation 1, we get the values. Fourier transform of sine 4 into 10 power 3 pi t by pi t equal to x of omega may be represented as 1 for modulus of omega is less than 4 into 10 power minus 3 and equal to 0 for omega is greater than the same frequency. So it is implied that Fourier transform x of t equal to x of omega, and the same may be equal to 0 for omega is greater than omega s by 2. Omega s by 2. So 4 into 10 power minus 3 by 2 pi. So you can have the Nyquist rate, because it is already been given as 2 into something else. I can have 4 into 10. This is the omega s. So the Nyquist rate will be omega s equal to 2 into this one. So 8 into 10 power 3 pi radians per second. So this is how I can calculate the Nyquist rate for the problem. So another problem. So suppose if the signal x of t having a Nyquist rate omega naught, determine the Nyquist rate for the continuous signal x square of t. So here also, because the signal is squared, what should be the sampling frequency or Nyquist rate we have? So same procedure I am considering. If the continuous time signal x of t with Nyquist rate omega naught, then Fourier transform of x of t equal to x of omega, and which may be equal to 0 for omega is greater than omega naught by 2. So here I am assuming y of t equal to x square of t. This is the problem given. So we know y of t equal to x square of t may be Fourier transform of this equal to y of omega may be represented as 1 by 2 pi x of omega with x of omega convolved with x of omega. So I can write like this. So it is clear from that we can only guarantee that y of omega equal to 0 for modulus of omega is greater than omega naught. Hence, the Nyquist rate for y of omega should be 2 into omega naught, because this is omega naught by 2 plus omega naught by 2. Two signals will be there. X of omega is 1, another x of omega. For x of omega, you have omega naught by 2. Another x of omega, you have another omega naught by 2. Omega naught by 2 plus omega naught by 2 equal to omega. Hence, the Nyquist rate of this equal to 2 into this one. 2 into omega naught, because 2 times the message signal frequency. Right? This is also similar to that what I have been given in the previous problem. So here x of t cos omega naught t. Similar way, y of omega equal to 1 by 2 x of omega minus omega naught plus x of omega plus omega naught. It is clear that we can guarantee that y of omega equal to 0 for modulus of omega is greater than omega naught plus omega naught by 2, because already x of t will have omega naught by 2, cos omega naught will give you omega naught. So omega naught plus omega naught by 2. So this will be 3 omega naught by 2. So thus the Nyquist rate of the signal y of t is 2 into 3 omega naught by 2, that is 3 omega naught. So this is the sampling frequency of Nyquist rate of the signal here. So here we have another problem. What it says is, here we are considering two signals x1 of t and x2 of t are sampled with a sampling frequency of 40 Hz. Obtain the associate time signal x1 of n and x2 of n and comment on the result. So what I am trying to do is, here x1 of t is being given as cos 20 pi t. So to convert this into discrete time signal, what I am trying to do is t equal to nt I am writing. So here the sampling frequency can be calculated given as 40 Hz, and from this 2 pi f1 equal to 20 pi, f1 equal to 10 Hz. So the x1 of n is obtained by replacing t by n by fs or nt. So fs is the sampling frequency equal to 40 Hz. So if I substitute, if I write the equation 2, you can write x1 of n equal to cos 2 pi f1 into n by fs. So cos 2 pi into f1 equal to 10, n by 40, cos pi n by 2. Similarly, if I do the same procedure for the next one, x2 of n equal to also cos pi by 2n, because here we have been got all cos 2 pi into for the second signal, this is cos 100 pi t. 100 pi t frequency is 50. 2 pi into 50 into n by 40. You can have cos 2 pi by 4 n. So you can have cos 2 pi into 1 plus 1 by 4 n. So if I simplify it, I can have cos pi by 2 n. So you can get the same signal as the previous one because of the aliasing. So the given sampling frequency fs equal to 40 Hz. Hence, the frequency contained in the signal should be less than or equal to fs by 2, that is less than 20 Hz. But it is not the case here. Therefore, the aliasing takes place. So here both sequences x1 of n and x2 of n are equal due to aliasing. Right? So this is the one which I have been explained. So thank you for listening to my words. Thank you, one and all.